What is light? The answer to this question is not that simple. It keeps changing as we explore various experiments and facts about this topic. In this video, we will understand light as a form of energy that enables us to see everything around us. The reason we call light as energy is that we receive light from the sun, which is the primary source of energy. Light behaves differently with various objects, and on this basis, objects are classified in three categories. The first category is opaque material that does not allow light to pass through them. Second category is translucent material that allows light to partially pass through them. Third category is transparent material that allows light to completely pass through them. Let's understand what ray of light means. It is the direction in which the light energy moves through a medium. Light in a given medium travels in a straight path, which is called rectilinear propagation of light. A ray of light is denoted by an arrow in the direction of propagation, and this branch of study is called ray optics. Now let's understand an important phenomena called reflection of light. Reflection is defined as the bouncing back of light to its original medium after striking on a smooth polished surface. The ray that travels from the light source to the polished surface is called incident ray. The ray that bounces back from the surface back to the original medium is called reflected ray. An imaginary line that is perpendicular to the reflecting surface is called normal. Angle found between the incident ray and the normal is called angle of incidence and is denoted by angle I. The angle between the reflected ray and the normal is called angle of reflection and is denoted by angle R. Evidently, the incident ray, reflected ray and the normal all lies in the same plane, and angle of incidence is always equal to angle of reflection. Let's understand what spherical mirrors are. Spherical mirrors are segments of a spherical glass ball. They are cut in the fashion as shown here. Now the arc obtained can be polished in one of the two ways. Number 1. If the inner portion is polished, the mirror so obtained is called convex. Number 2. If the outer bulge is polished, the mirror is called concave. Next term is center of curvature, which is denoted by C. It is the geometric center of the sphere from where the mirrors are obtained. The second term is radius of curvature, denoted by R. It is the radius of the spherical ball. The next term is the pole, denoted by P, which is the center of the polished mirror. Next term is aperture, which is defined as the chord AB that is found by joining the endpoints of a spherical surface. Next, we define a straight line that passes through pole and center of curvature called as principal axis. Now, if we pass number of rays parallel to the principal axis, all these rays will meet at a specific point on the principal axis. This particular point is known as focus and is denoted by F. The distance between pole and focus is called focal length and is denoted by small f. Since the distance between pole and center of curvature is called radius of curvature, which is denoted by R, there is a relationship between radius of curvature and focal length, which is R is twice of F. We will derive this relation in some other video. For the time being, just keep this relation in mind. These terms will be same for convex mirror, except for the fact that concave mirror is converging, that is, rays meet at a point after reflection, whereas convex mirror is diverging, that is, rays spread outwards after reflection, and rays do not actually meet at a point but appears to be coming or originating from a point. This point is called the focus of a convex mirror. Note that focus of convex mirror lies behind the mirror. The relation R equals twice of F still holds true for convex mirror. After understanding all the terms, we are now in a position to discuss the image formation by the spherical mirrors. An image is found when there is an intersection of more than one reflected rays. Before we move further, let's understand some important rules that light rays obey. According to rule 1, light rays parallel to the principal axis meet or appear to be coming from the focus of the mirror after reflection. Rule 2 states that light rays that pass through the focus emerge parallel to the principal axis after reflection from the mirror. According to rule 3, a light ray that passes through the center of curvature reflects back or retraces its original path. Rule 4 states that when a light ray is obliquely incident on the pole, the light ray follows the laws of reflection. That is, it reflects along the same angle as the angle of incidence. That is, angle I equals angle R. As per rule 5, light ray normal to the mirror always passes through the center of curvature. These rules are also valid for convex mirror. These rules will be applied to form ray diagrams. Let's begin with the concave mirror. Case 1. When object is placed at infinity. For this case, we cannot actually place an object on the principal axis. Instead, rays are assumed to be coming as parallel to the principal axis. Therefore, by using rule 1, these rays will meet at focus. The point of intersection is where the image is formed. It is clear from the diagram that image is formed, number 1, at focus, number 2, is highly diminished, that is point sized, number 3, is real, that is, it is formed in front of the mirror and can be obtained on a screen. For the next case, we will place the object beyond C, that is center of curvature. This object can be a pencil, penguin or a star, but in ray diagrams, an upright arrow is used. For this case, 3 incident rays are shown. First parallel to the principal axis, second at pole and third at focus. By the application of respective rules, an image is obtained between focus and center of curvature, which is diminished in size and is real and inverted. Next case is when the object is placed at C, that is center of curvature. We again incident the same 3 rays and obtain an image at C, which is of the same size and is real and inverted. Next case is when the object is placed between center of curvature and focus. For this case, image is formed beyond C, which is enlarged, real and inverted. If the object is placed at focus, we see the reflected rays will meet at infinity. The image formed will be highly enlarged, real and inverted. For the last case, the object is placed between pole and focus. In this case, the rays will not meet in front of the mirror but appear to be coming from behind the mirror. The images so formed are called virtual, which can't be obtained on the screen. The image is enlarged and erect. For convex mirror, there are just 2 cases. Case 1 is when the object is placed at infinity, then the rays appear to be coming from the focus behind the mirror. The image is point-sized, virtual and erect. For the second case, the object is placed anywhere between infinity and the pole. We will always obtain an image between pole and focus, which is diminished, virtual and erect. There are set of sign conventions that must be followed while dealing with the reflection of light by the spherical mirrors. These are: number 1, always place the object left of the mirror. Number 2, all the distances are measured from the pole, so it acts as origin. For example, we want to know the distance of object AB, so it must be said PA, not AP. Number 3, distances that are measured to the right of pole are positive, while the distances measured to the left of pole are negative. Number 4, heights measured above the principal axis are taken as positive, while below the principal axis are taken as negative. Relationship between focal length and radius of curvature for spherical mirrors. Let's first derive it for concave mirror. There are 2 ways of deriving it. Let's see the first one. Consider a concave mirror with center of curvature C, focus at F and pole at P. The first step is to draw a normal on the mirror, as any normal to the mirror passes through the center of curvature. Then incident a ray AB parallel to the principal axis on the mirror. As any ray parallel to the principal axis passes through the focus, therefore this ray AB must pass through focus. Now the angles made by the incident ray AB and reflected ray BF make equal angles with the normal in accordance with the laws of reflection. Let these angles be theta. Now angle BCP should also be equal to theta, as interior alternate angles are equal. Now in triangle BCF, side BF must be equal to side FC, as sides opposite to equal angles are equal. Assume the aperture of the mirror to be small. The approximation of segment BF can be taken as segment FC. Therefore, we can write segment PF equals segment FC. Now adding PF on both sides to this equation, we get PF plus PF equals PF plus FC, which becomes twice of segment PF equals PC. As segment PF is equal to focal length F and PC is equal to radius of curvature, that is R. Therefore, the relation becomes twice of focal length equals radius of curvature, which is the required relation. Moving further, let's understand the proof of the above relation using trigonometric ratios. Though this method is slightly technical and requires the knowledge of basic trigonometric rules, it is suitable for higher classes. The method begins with the construction of normal on the mirror which passes through point C. Next, consider an incident ray AB parallel to the principal axis, which after reflection passes through point F. The incident ray and the reflected ray makes equal angle theta with the normal in accordance with the laws of reflection. Angle BCP will also be equal to theta because interior alternate angles are equal. Angle BFP will be twice of theta because exterior angle of a triangle is equal to the sum of its interior opposite angle. Next, construct BN normal on the principal axis so that a right angled triangle BNC is obtained. Now we will find tangent of angle theta, which is given as the ratio of perpendicular and base in a right angled triangle. Substituting the values of perpendicular and base, we get tangent of theta equals ratio of segment BN to segment NC. Name this equation as equation 1. Now consider another right angled triangle BNF and find tangent of 2 theta in this triangle. Tangent 2 theta equals ratio of segment BN to segment NF. Name this equation as number 2. Now on dividing equation 2 by equation 1, we get tangent of 2 theta divided by tangent of theta equals ratio of segment BN to NF divided by ratio of segment BN to NC, which can be simplified as Bn upon Nf multiplied by Nc upon Bn. On simplifying Bn with Bn, we are left with tangent of 2 theta divided by tangent of theta equals segment Nc upon segment Nf. Since aperture is small, so approximation of segment Nc is considered as segment PC, which is equal to R, and segment NF is considered as segment PF, which is equal to F. Since angle theta is also small, therefore tangent 2 theta is approximated as 2 theta and tangent theta is approximated as theta. On substituting the corresponding values, the above equation becomes 2 theta upon theta equals R upon F, which on further simplification becomes 2 equals R upon F. On cross multiplication, we get R equals twice of F, which is the required relation. Now moving on to the case of convex mirror. Let's see the first method. Consider a convex mirror with center of curvature C, focus at F and pole at P. Draw a normal on the mirror which passes through the center of curvature C. Note that for convex mirror, center of curvature lies behind the mirror. A ray AB parallel to the principal axis is incident on the mirror, which reflects and appears to be coming from the focus F. The angle of incidence is equal to angle of reflection in accordance with the laws of reflection. Let these angles be theta. Now angle BCP should also be equal to theta as corresponding angles are equal. Also angle CBF equals theta as vertically opposite angles are equal. In triangle BCF, BF must be equal to segment FC as sides opposite to equal angles are equal. Assume the aperture of the mirror to be small. The approximation of line segment BF is taken as segment PF. Therefore, we can write segment PF equals segment FC. Now adding PF on both sides of this equation, we get PF plus PF equals PF plus FC, which becomes twice of PF equals PC, as PF is equal to the focal length F and PC is equal to the radius of curvature R. Therefore, the relation becomes twice of focal length equals radius of curvature R, which is the required relation. Moving further, let's understand the proof of this relation by using trigonometric ratios. The method begins with the construction of normal on the mirror which passes through point C, which lies behind the mirror. Next, a ray AB parallel to principal axis is incident on the mirror which reflects and appears to be coming from the focus F. The angle of incidence is equal to angle of reflection in accordance with the laws of reflection. Angle BCP equals theta and angle BEP equals 2 theta as corresponding angles are equal. Next, construct BN normal to the principal axis. In right angled triangle BNC, tangent of theta will be given as Bn upon Nc, and in right angled triangle BNF, tangent of 2 theta will be given as Bn upon Nf. On dividing equation 2 by equation 1, we get tangent of 2 theta upon tangent of theta equals Bn upon Nf divided by Bn upon Nc. On simplification, which can be written as Bn upon Nf multiplied by Nc upon Bn. On simplification of Bn with Bn, this reduces to Nc upon Nf. Since aperture is small, Nc can be approximately be written equal to Pc, which is equal to R, and Nf can be written equal to Pf, which is equal to the focal length F. Also, tan of 2 theta can be approximated as 2 theta and tan theta can be approximated as theta. Therefore, above expression becomes 2 theta upon theta equals R upon F. On simplification, we get 2 equals R upon F. On cross multiplication, we get R equals twice of F. Hence, radius is twice of focal length. Derivation of relation between the object distance, image distance and the focal length of spherical mirrors, which is known as the mirror formula. Let's first see the case of concave mirror. Consider a concave mirror having pole P, focus F and center of curvature C. An object AB is placed beyond C. A ray parallel to principal axis is incident on the mirror that passes through focus. Another ray is passed through C that retraces itself along the original path. At last, a ray is incident at pole that is reflected along the same angle in accordance with the laws of reflection. The point of intersection is where the image will be formed. Since it lies below the principal axis, the image is inverted. It can also be seen that image is diminished in size. Label this image as A-B'. Now using the sign conventions, focal length is FP and lies left to the pole. Therefore, it is equal to -f. Similarly, the radius of curvature PC equals -r. The object AB also lies left of the pole. Therefore, object distance, that is PB, equals -u. The image distance PB' is equal to -v. Now consider triangle ABC and triangle A'-B'(C), which are similar to each other. Since the ratios of corresponding sides of similar triangles are equal, therefore the ratio of A'-B'(C) to AB is equal to ratio of B'(C) to CB. As all distances are measured from pole, therefore B'(C) can be written as PC minus PB' and CB can be written as PB minus PC. Substitute these values to obtain ratio of A'-B' to AB equals -r plus V upon -u plus r. Also, triangle ABP and A'-B' are similar. Therefore, ratio of A'-B' to AB equals ratio of PB' to PB. On substituting the values of PB' and PB, we get A'-B' upon AB equals V upon U. Equating the RHS of equations 1 and 2, we get -r plus V upon U plus R equals V upon U. On cross multiplying, we get -UR plus UV equals -UV plus VR. On transposing the like terms, we get UR plus VR equals 2UV. On dividing by UVR throughout, we get 1 upon V plus 1 upon U equals 2 upon R. Since R is twice of focal length, therefore the above equation becomes 1 upon V plus 1 upon U equals 1 upon F, which is the required relation. Moving on to the case of convex mirror. Consider a convex mirror with pole P, focus F and center of curvature C. AB is an object that is placed in front of the mirror. A ray is incident parallel to the principal axis. This ray is reflected outwards by the convex mirror. On producing it back, it meets at focus F. Second ray is normal on the mirror, which appears to be reflecting from C. The third ray is incident on the pole, which reflects according to laws of reflection. Producing it backwards, it intersects the first two rays to form an image at A'-B'. Since the intersection point is above the principal axis, therefore it is an erect image. Also, the image is diminished in size. Now using the sign conventions, we get focal length PF, which lies to the right of pole, therefore is taken as positive and is denoted by F. Similarly, the radius of curvature is also positive and is equal to R. The object lies to the left of the pole, therefore object distance PB is equal to -u. The image distance PB', which lies to the right of pole, is taken as positive and is equal to positive V. Now triangle PBC and triangle A'-B'(C) are similar. Therefore, the ratios of corresponding sides of these triangles will also be equal. So ratio of A'-B' to AB is equal to ratio of B'(C) to CB. As B'(C) is equal to PC minus PB' and CB equals PB plus PC, on substituting the values we get A'-B' upon AB equals R minus V upon -u plus R. Also, triangle ABP and triangle A'-B' are similar. Therefore, ratio of A'-B' to AB equals ratio of PB' to PB, which is further equal to V upon -u. On equating the RHS of the equations 1 and 2, we get R minus V upon -u plus R equals V upon -u. On cross multiplying, we get -UR plus UV equals -UV plus VR. On transposing the like terms, we get UR plus VR equals 2UV. Dividing by UVR throughout, we get 1 upon V plus 1 upon U equals 2 upon R. Since radius is twice of focal length, therefore the above equation becomes 1 upon V plus 1 upon U equals 2 upon 2F. On simplifying, we get 1 upon V plus 1 upon U equals 1 upon F, which is the required relation. Relationship for linear magnification of spherical mirrors. Linear magnification is defined as the ratio of height of image to that of the object. It is denoted by m and equals h2 over h1, where h2 is the height of image and h1 is the height of object. Let's now derive a relation for m in terms of u and v,
where u represents distance of object from pole, whereas v represents the distance of image from the pole. Let's first see the case of concave mirror. Consider a concave mirror with pole P, focus F and center of curvature C. An object AB is placed beyond C. The light ray parallel to the principal axis passes through the focus F. The light ray through the center of curvature C retraces its path after reflection, and the ray at the pole reflects according to the laws of reflection. All these rays meet at a point to form an inverted image denoted by A', B'. According to the sign conventions, the height of the object AB equals positive h, while the height of the image A', B' equals minus h2, since image is formed below the principal axis. The object distance equals minus u, since it lies left to the pole, and the image distance equals minus v for the same reason. Since triangles ABP and triangle A', are similar, therefore the ratio of their corresponding sides are proportional. So, ratio of A', B' to AB equals ratio of PB' to PB. Putting the corresponding values, we get minus h2 over h1 equals minus v over minus u. On simplification, we have minus h2 over h1 equals v over u. Since h2 over h1 equals m, therefore m equals minus v over u. For the case of convex mirror, consider a convex mirror with pole P, focus F and center of curvature at C. Object AB is placed in front of the mirror. A ray passing parallel to principal axis diverges and appears to be coming from the focus. The ray incident on center of curvature reflects back along the same path. The ray incident on pole diverges in accordance with the laws of reflection. When reproduced backwards, these rays appear to meet behind the mirror. The virtual and erect image is formed at A', B'. Now, according to the sign conventions, the height of the object AB is positive h1, the height of the image A', B' is positive h2, as both are above the principal axis. The distance of object PB equals minus u, as it lies left to the pole. The distance of image PB' equals positive v. Now consider triangle ABP and triangle A', B', as the triangles are similar. Therefore, ratio of A', B' to AB equals ratio of PB' to PB. Putting the values, we get h2 over h1 equals v over minus u. Since h2 over h1 equals m, therefore m equals minus v over u, which is the required relation. Since linear magnification is same for both the mirrors, we can derive magnification in terms of u and f, where u represents the distance of object and f represents focal length. As mirror formula equals 1 upon f equals 1 upon v plus 1 upon u, multiplying this equation by u, we get u over f equals u over v plus 1. On transposing, we have minus u over v equals 1 minus u over f. Taking LCM, we have minus u over v equals f minus u over f. On taking reciprocal both sides, we get minus v over u equals f over f minus u. Since magnification equals minus v over u, therefore m equals f over f minus u. To obtain the relation in terms of v and f, that is distance of image from the pole and focal length, multiply the equation of mirror formula by v throughout, we get v over f equals 1 plus v over u. On transposing, we have minus v over u equals 1 minus v over f. Taking LCM, we get minus v over u equals f minus v over f. As minus v over u equals m, therefore we have m equals f minus v over f, which is the required relation. The difference between real and virtual images formed by spherical mirrors. Before we understand the differences, let's quickly recap how spherical mirrors work. When light rays reflect off a spherical mirror, light rays obey certain rules. For a concave mirror, rays parallel to the principal axis converge to a point known as the focal point, while for a convex mirror, they diverge as if coming from a focal point. Now let's discuss real images. Real images are formed when actual light rays intersect in front of the mirror at a specific point, resulting in a clear image that can be projected onto a screen. On the other hand, virtual images are a bit different. They are formed when light rays appear to intersect behind the mirror, even though they don't actually converge at that point. These images cannot be projected onto a screen because they don't actually exist in physical space. Virtual images are like optical illusions. They appear to be there, but you can't physically touch or capture them. A real image is always inverted, whereas a virtual image is always erect. A real image is formed by only concave mirror. However, a virtual image can be formed by concave, convex and plane mirror also. This table summarizes all the differences. Both concave and convex mirrors may seem like ordinary objects, but they play crucial roles in ensuring safety and convenience in various scenarios. Let's dive into how they are utilized. First up is concave mirror. These mirrors are fantastic for focusing light and producing detailed images. Shaving mirrors. Shaving mirrors are more than just reflective surfaces. They are precision tools designed to provide a clear and magnified view of our faces. And at the heart of many shaving mirrors lies a concave mirror. Headlight of a car. Headlights are more than just illumination devices. They are critical for ensuring safe driving, especially in the low lighting conditions, and concave mirror play a vital role in optimizing their performance. Ophthalmoscope. Ophthalmoscopes are major tools used by the doctors to examine the interior structure of the eye, such as retina, optic nerve, and blood vessels. It is basically just a concave mirror. The concave mirror controls the angle and intensity of the light beam. This control is essential for achieving optimal visualization without causing discomfort to the patient. Now let's see the practical application of convex mirror. Since convex mirrors always produce an erect and diminished images of the object, therefore they are used as rear view mirrors in the vehicles, enabling the driver to see the traffic behind to facilitate safe driving. These mirrors provide the wider field of view of the traffic behind the driver. It is also used as reflector for street lights. Let's continue with the first one. The problem states, a convex mirror is used for rear view on an automobile has a radius of curvature of 3 meter. If a bus is located at 5 meter from this mirror, find the position, nature and size of the image. We begin by constructing the ray diagram for the problem. Since the mirror is convex, the ray diverge and create a virtual image which is erect and diminished. In order to find the position of the image, we will use the mirror formula, which is 1 upon f equals 1 upon v plus 1 upon u. Since focal length equals half of radius of curvature, therefore putting the value of radius of curvature as 3, we get focal length equals 3 by 2 or simply positive 1.5 meter. As for convex mirror, focus lies behind the mirror. Here u, that is distance of object, is negative and is given as minus 5 meter as it lies to the left of the pole. We need to find the value of v, that is the distance of image formed. Putting the values into the mirror formula, we have 1 upon 1.5 equals 1 by v minus 1 by 5. On transposing, we have 1 upon v equals 1 upon 1.5 plus 1 upon 5. Taking LCM, we have 1 upon v equals 5 plus 1.5 over 7.5, which gives us 1 by v equals 6.5 over 7.5. Now taking reciprocal on both sides, we get v equals 7.5 over 6.5, which gives us v as 1.15 meter. We can verify that the position of image is correct as the value of v is positive since image lies to the right of pole in the ray diagram. In order to find the size of image, we will make the use of relation of magnification, that is m equals h2 over h1 equals minus v over u, where h2 is the height of the image, so h2 equals minus v over u into h1. Putting the values, we get h2 as minus 1.15 divided by minus 5 into h1. On simplifying, we have h2 as 0.23 into h1. Therefore, the image is smaller by the object by a factor of 0.23. Moving on to the next problem. The problem states, an object 4 cm in size is placed at a distance of 25 cm in front of concave mirror of focal length 15 cm. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Find the nature and size of the image. The distance of the screen basically means the distance of the image from the pole. We will again make the use of mirror formula, but first let's draw the ray diagram for the problem. The height of the object h1 is positive 4 cm as it lies above the principal axis. The distance of the object u is minus 25 cm as it lies to the left of the pole. The focal length of the mirror f is minus 15 cm as the mirror is concave. Putting the values in the mirror formula, we have minus 1 upon 15 equals 1 upon v minus 1 upon 25. On transposing, we get 1 upon v equals 1 over 25 minus 1 upon 15. On taking LCM, we get 1 upon v equals 3 minus 5 over 75, which equals minus 2 over 75. On taking reciprocal on both sides, we get v as minus 37.5. Negative sign indicates that the image lies left to the pole, which can be verified by the ray diagram. To find the size of the image, we make the use of relation magnification equals h2 over h1 equals minus v over u. Therefore, h2 equals minus v over u multiplied by h1. On putting the corresponding values of v, u and h1, we get h2 equals minus into minus 37.5 over minus 25 multiplied by 4. On simplification, we have h2 equals minus 6 cm. Negative sign indicates the image is inverted and negative magnification indicates that the image is real. Moving on to the next problem. The problem states that an object is placed at a distance of 10 cm from a convex mirror of focal length 15 cm. Find the position and the nature of the image formed. For a convex mirror, the focal length is positive, and in this case it is positive 15 cm. As the object is always placed in front of the mirror, so the distance of object u equals minus 10 cm as it lies left to the pole. Now putting the corresponding values in the mirror formula, we get 1 upon 15 equals 1 upon v minus 1 upon 10. On transposing, we get 1 over v equals 1 over 15 plus 1 over 10. On taking LCM, we get 1 over v equals 2 plus 3 over 30, which is simplified as 5 over 30. On taking reciprocal on both sides, we get v equals 6 cm. As convex mirror always produces a virtual and erect image, so nature of this image will also be same. Moving on to the next problem. The problem states that an object 5 cm in length is placed at a distance of 20 cm in front of convex mirror with radius of curvature 30 cm. Find the position of the image, its nature and the size. Using mirror formula, that is 1 over f equals 1 over v plus 1 over u. Since radius of curvature is twice of focal length, therefore focal length equals half of radius of curvature, which is positive 15 cm for a convex mirror. Distance of object u equals minus 20 cm. To find the position of image, put the corresponding values in the mirror formula to get 1 over 15 equals 1 over v minus 1 over 20. On transposing, we have 1 over v equals 1 over 15 plus 1 over 20. By taking LCM, we get 1 over v equals 4 plus 3 over 60, which equals 7 over 60. Taking reciprocal on both sides, we get v equals 60 over 7, which is simplified as 8.57, which indicates the image lies to the right of pole. To find the size of image, we make use of relation m equals h2 over h1 equals minus v over u. Simplifying for h2, the equation is reduced to minus v over u into h1. On putting the corresponding values of v, u and h1, we get h2 equals 8.57 divided by minus 20 into 4, which is simplified as 2.14 cm. As the sign of h2 is positive, therefore the image is erect and diminished, as is clear from the comparison with the height of the object. Moving on to the next problem. The problem states that an object of size 7 cm is placed at 27 cm in front of concave mirror with focal length 18 cm. At what distance from the mirror should a screen be placed so that a sharp focused image can be obtained? Find the size and nature of the image formed. Here the height of the object is h1, which is equal to 7 cm as it lies above the principal axis. The focal length of the mirror is minus 18 cm. The distance of object is u, which equals minus 27 cm. The distance of the screen is equivalent to the distance of image, so using the mirror formula, that is 1 over f equals 1 over v plus 1 over u. Putting the corresponding values of f and u, we get minus 1 over 18 equals 1 over v minus 1 over 27. On transposing, we get 1 over v equals 1 over 27 minus 1 over 18. Taking LCM we get 1 over v equals 2 minus 3 over 54, which on simplification becomes minus 1 over 54. On reciprocal we get v as minus 54. Thus the image lies 54 cm in front of the mirror. To find the size of the image, use m equals h2 over h1 equals minus v over u. On putting the corresponding values of h1, v and u we get h2 equals minus into minus 54 over minus 27 multiplied by 7. On simplification, h2 equals minus 2 into 7, which equals minus 14 cm. Here negative sign indicates that the image is real and inverted. Moving on to the next problem. The problem states that we wish to obtain an erect image of an object using a concave mirror of focal length 15 cm. What should be the range of distance of the object from the mirror? What is the nature of the image? Is the image larger or smaller than the object? Draw a ray diagram to show the image formation in this case. It is a known fact that concave mirror produces an erect image only when the object is placed between pole and focus. Therefore, the range to obtain an erect image will be 0 to focal length. Focal length is given as 15 cm, therefore the range comes out to be 0 to 15 cm. So this was it for the video. See you in the next one. Thank you for watching.